Vikas, kindly confirm. Okay, recording has been started. Okay. Vikas, please
Yeah, sir.
start. Yeah.
Yeah. Uh, Good day to everyone. My name is Vikas Medari, pursuing an MTech in Computer-Aided Structural Engineering at IIT Hyderabad. I feel honored to extend my warm welcome to all present here. On behalf of IIT Hyderabad Student Chapter, I want to take this opportunity to welcome our guest speaker, faculty, scholars, the research fraternity, the industry professionals, and all the students to join the online session on the topic Design of Structural Steel Systems as per IS 18168-2023. It is my privilege to introduce our guest speaker, Dr. PC Ashwin Kumar. He is an assistant professor in the Department of Earthquake Engineering, IIT Roorkee. He holds a BTech from GEC Thrissur and a MTech from IIT Madras and a PhD from IIT Delhi. His research mainly focuses on the seismic response and the design of steel structures, supplemental damping and energy dissipation device, and a large-scale structural testing and simulations. With over 8 years of research experience, Dr. Ashwin Kumar has published extensively in reputed international journals and conferences. He currently supervises 9 PhD scholars and has completely 3 sponsored research projects and continued to lead several others. Additionally, he has contributed to numerous consultancy projects for government and public sector organizations. Dr. Ashwin Kumar has served as Associate Dean at IIT Roorkee and was the organizing secretary of the 17th Synopsism on Earthquake Engineering. He is a life member and secretary of ISET and an affiliate member of ASCE. We are truly privileged to have him with us today. Before we start, a small announcement for all the participants. If you have any questions or clarification during the session, please type them in chat box. We'll address them in the question and answer session at the end, moderated by Dr. Praveen Kumar Venkatrao, Faculty Advisor of Student Chapter. Now, without any further delay, we'll turn the time over to our speaker. Sir, over to you.
Thank you, Vikas, and thank you, Dr. Praveen, for this opportunity. It's a very auspicious day since our IS 1893 Part 1 has been published,
Yes.
and
Sir.
that is also kind of giving relevance to this particular talk, wherein the structural steel systems like EBF, SCBF, and MRF are being put onto the spotlight. So, since it's a 1 hour lecture, I want to kind of introduce the audience to the IS 18168 code as to what it really does and how it goes about. So I'll be I'll keep my pace in such a way that you understand the basic concepts, so that when you open the code, you'll be able to understand what clauses mean, etc. Right? I will not go into clause by clause. So you know that IS 800 2007 is already there for design of steel structures, wherein we use limit state method, right? In that, if you have seen structural system per se, like MRF, CBF, and EBF systems, is being explained. More or less, it is like tension member, compression member, and all those other design of forces like column, design of beams, etc. is given. But structural system per se is given section 12, right? So, but section 12, if you open and see, if you have to design these systems, it's a 1.5 page kind of a detailed. It's only a very limited explanation is given for these systems. But recently, IS 18168 in 2023 has come about, wherein these systems have been explained in detail. Specifically, with respect to when you look at steel buildings and all, we kind of rationalize it as it is good performing in high seismic region. So accordingly, in IS 18168, it is specific for earthquake resistant design and detailing of steel code building, right? Steel building code of practice. So you have these nomenclatures like MRF, SMRF, CBF. In terms of that, it's written as SCBF, which is nothing but moment resisting frame, and this is special moment resisting frame. The same kind of nomenclature that we have in RCC, wherein we say special moment resisting frame is because of the detailing practice, whereas nothing else changes in terms of the overall behavior of the structural member in seismic thing. Nothing changes here also. It is the detailing or the connection practices or detailing practices that we have to follow, which makes them special. So this is what this new code is totally about. It talks about these three structural systems, how to design them, what are the different clauses that you have to follow, etc. is given in this particular code. Now, applicability of this code: steel buildings located in seismic zone 3, 4, and 5, residential, educational, and institutional building, office and business building, community, utility, lifeline buildings. And it's optional whether you want to use it in zone 2 or not, that is optional to you. Now, few things: in zone 5, only EBF system, eccentrically braced frame system, shall be used. So The audience, I want you to understand that there is something good about the EBF system. That is why it is being specified for zone 5. The next is zone 5 SCBF, special concentrically braced frame shall not be used. So there is something wrong about the performance of special concentrically braced frame, that even after being special, it is not being permitted to be used in zone 5. So we'll see what those problems are. And then in zone 5 and 4, SMRF buildings of less than 15 meter is allowed. You understand why that is for, because of the stiffness issue, that moment resisting frame as such, a solo moment resisting frame have less amount of stiffness. So above 15 meters, the stiffness becomes the more of a problem. So it is like, okay, you go for less than 15 meters, zone 5 and zone 4, you can use it. That is what is given in IS 18168. It will be a little bit different from what is currently established in 1893 part 1 of part 1 and 5 of 2025 as such. So we'll keep it to 18168 right now, and all steel frames in a building need not be designed for earthquake load. So this is a little bit new. We'll come back to it later on in this thing. It says not every frame needs to be, not every element or every frame needs to be seismic force resistant. You can design few to be seismic force resistance, and the rest of can be gravity load resisting members. So we'll come to it later on in that essence. Now, at the concept level, you have to understand that this 18168 is nothing against or a new method or something like that. It's not giving with respect to design of steel structures. You were using IS 800 2007 limit state method. Now also you will use IS 800 2007 for designing the members. This code, in terms of the capacity design concept, brings about how to assess the forces in the members. So the important aspect is how to assess what is the bending moment, shear force or axial force in a member. And once you've assessed it correctly based on the capacity design approach, you go into designing of those members based on IS 800 2007 limit state method. That's it. And you already know the capacity design. All your teachers, once they talk about this capacity design, they would have always shown this chain kind of link kind of structure, where they say that in capacity design, we design the weakest link to be the most ductile, and rest of the members that are there, these big ones, are designed for the higher strengths, as that you don't depend upon ductility onto the system. That is why we call them as brittle, like it's very high strength, it has a high strength, high elasticity, etc. And then the elastic strength, I mean, in terms of yield strength and all, will be much higher than what this ductile member will be having. So the weakest member designed for the adequate required force is to be the most ductile, so that when I pull it, all the damage and energy dissipation happens in the weakest link. That is a capacity design approach. Now, this would be the most important slide that you have to remember throughout this particular course that I'm going to, this lecture I'm going to take. So now there is a force controlled element, there is a deformation controlled element. The thing I'm saying is, suddenly I said deformation control and force control element. The deformation control element is a designated element, that is in which we are not bothered about how much the force is going to come, etc., but we are bothered about how much amount of deformation it can take, which means I'm more dependent upon the ductility of that particular system, which means it is the energy dissipating element, that element is going to yield. It has to be ductile so that it is able to deform much more without any failure. So the deformation controlled element is the most important element, or this particular, the deformation control element is symbolized by this ductile element in this capacity design method. And the force controlled element is the one where we want the forces to be within the limits, such that it does not exceed this tipping point shown in this particular graph. So please understand, deformation controlled element is on which we depend upon that they are the ones who dissipate the energy through yielding or nonlinear activity during an earthquake, where deformation or ductility is more important. Those members are the deformation controlled element, and the ones, those brittle elements in the name, in the capacity link chain, who are the brittle elements or the stronger elements, are the ones where we more depend upon the forces, like what are the maximum force that comes into it should be below a certain limit, right? So in this particular image, there are three systems: the SMRF system, the CBF system, and the EBF, eccentrically braced system. And identify by the color. Later on in the lecture, I'll say the green element or the black element. You have to identify it as the green elements are the deformation control elements. You can understand, right? In a moment resisting frame, we are designing for strong column, weak beam, etc. So we are making the beam weaker in a general sense, that all the energy dissipation or the yielding or everything happens in the beam. That is why that is green in color here. So if you look at in the same way for the CBF system, the green color is the braces, which means we want the nonlinearity or the inelasticity to happen in the braces. when the earthquake comes, and we want mostly the beams and columns to be elastic. That is the meaning of this. And in eccentrically braced frame, if you see the small link, the eccentric link that you have here is the energy dissipating element. Rest of even brace here, beams and columns are the brittle element in the capacity chain link. That is what I'm saying. When I say brittle, don't say it as brittle, but it's like the more stronger member, which is not meant to yield or easily yield during a seismic wave, right? So if this is clear, we will move forward. So I have deformation control element, the heroes of the story. The force control element, which are the more important one in terms of the structural stability. I want those guys to survive so that there is not much of a damage. Before going into the structural system, one thing is with respect to material grade selection. So as per 18168, what is a grade of steel that we can use in our structural steel structural system is given as E250, E275, E300 and E350, right? You can see a B0, C, all those categories are given, but the crux of it is that you can use a material grade up to E350, which means E350 is the yield strength, the nominal yield strength of the structural steel allowed to be used in structural steel systems like MRF, CBF, and EBF is 350 MPa. That is the case of it. Now, if you look into IS 2062, the code which gives about the material grade and their chemical composition and mechanical property limits, if you see here up to E350, you have again A, BR, B0, and C. We'll come to that soon. You have these yield strength, nominal strength for less than 20 mm plate is 350 MPa. Then there are percentage elongation is minimum is 22% that is required. And there is a CHARPy requirement, the CHARPy energy to be 27 joules for room temperature 0 degrees Celsius and minus 20. If you go above 410, 450, all grades are available, but you can see the CHARPy energy dropping down a higher notch, and the minimum 22% is also getting reduced in the higher strength steel as expected. Now, as I said, there is a subcategory of the grade of steel, like E250 has a grade of B0 or C. What is the meaning of that is you have four subcategories. If you can see above here, there is A, BR, B0, and C. A is for it's like for simple structures. If you're building up a temporary shed, non-important structures, etc. with steel, you can go for a category A type of a steel, which is of a low cost. Normally in India, we go for category B0 or BR. B0, why do we say that? Is when if you're building up a structure which is not temporary, like a temporary shed or something like that, it's a building where there is a possibility that the temperature may be nearer to maybe sub-zero, like Delhi, where not sub-zero, like 3 degrees Celsius or something like that. Colder climate, you go for a B0 where there is a minimum requirement of the CHARPy test to be done at 0 degrees Celsius. And BR is where the impact test is to be done at room temperature, where you're like, okay, the temperature, this is with respect to ductile to brittle transition. A steel metal, when it gets colder, it becomes more brittle. So if you are in an environment where the temperature is going to go down, you have to be very careful in terms of the selection of this subcategory of the steel. So if you are going into, let's say, Himalayas, on top of Himalaya, you want to build a steel structure, etc., the category C would be the most ideal, as it assures you a certain level of CHARPy value at minus 20 degrees Celsius. Like it is like mandatorily telling you, do the CHARPy test. That is how you will be able to. So as you see, as the category goes down, the cost also will increase because you're asking for more performance from the steel. Like give me higher energy at minus 20 degrees Celsius. The energy due to that impact test that you do under CHARPy, right? Then you have mill test report. Like I have kept SAIL report here. A mill test report is something that you engineers, the students and everyone has to be very careful about, which gives a detail about when you buy a steel from a vendor, you have to be very careful about what is the property of steel that you get. So this is a mill test report from a particular lot that they have. They have given the chemical composition. They have given what is the size of the plate, what is the thickness of the plate, and then they have given what is the yield strength that they have got from it. So this is the tested value. This is not the nominal value. So if you're buying a grade of E350, they will test it. They will say in this lot, when I did the coupon test, I'm getting the value of the tensile yield strength to be this much. So this is the tested value. So it is giving you, okay, my percentage elongation is also about 20 to 22%. So this is okay. Then my CHARPy value at different temperatures at minus 20, then at normal level is again about 27 joules. So it qualifies my requirement. So this has to be ensured. If you buy from a local vendor, you might not know these values and you might be under designing or the material may be underutilized or overutilized based on what the actual grade would be, but a mill test report gives a certificate as to what you're buying, right? Now, if you look at IS 18168, one more thing it says, okay, E350 grade is the maximum that you require, but you need certain properties. Like, as I said, minimum percentage elongation is 22%. Now, 22% is a direct measurement of the ductility of the steel, right? You test the steel under monotonic test under a UTM machine, and you measure the percentage elongation over the gauge length. So minimum that would be 22%. Then it says the structural steel should have a minimum Charpy value of 27 joules at 0 degrees Celsius. And then ratio of ultimate to yield strength shall be 1.15. This is there in rebar also. In rebar also, the minimum 1.15 ratio is also mentioned in there. So we'll get to know what these things are. So coupon test, just to have the audience, whether students who have not witnessed, there is a coupon test. This is the gauge length. You have a grip in which it is being pulled, and it breaks in the gauge length area, means you have a valid coupon specimen over which you measure what is the percentage elongation, yield strength, and ultimate strength. This is the Charpy test, which you would have done in your undergraduation, where you have done the Charpy test in terms of the pendulum being moving and striking a notched sample, and then based on what is the energy that is absorbed or during the test is measured, and that is being given as 27 joules. Now, an FU by FI. So understand this, that once again I'll slow down. In terms of percentage elongation is a direct measurement of ductility. Charpy value, the relevance of why, I mean, if you are already saying that 22% elongation is what measures ductility, why is there a need to do Charpy test? Charpy test is important in a way that when you do welding, when you do some kind of joining exercise, or even the metal when is formed during the manufacturing process, there is a possibility that there may be some initial voids or porosity, or some while joining there may be some notches that is created. So let's say there is an initial crack already present in the steel. Now, Charpy test is like fracture toughness measurement. It says if you have a crack, if your Charpy value is less, the opening or propagation of the crack becomes very fast if your Charpy value is less than a certain number. If it is more, even if you have a crack, see, if you weld any steel, the process is not like completely flawless. It will have some flaws, porosity, slag inclusions, anything and everything can come in. So there is no point of looking at a fracture initiation time. So there is already some kind of crack there. You want some kind of life in it. So when you look at bridges or buildings, there is always Charpy coming up again and again, which is a kind of fracture toughness in the material. So 27 joules in, let's say, room temperature or 0 degrees Celsius is a guarantee that you have, that if you have a crack, it will not propagate quite quickly into a complete failure. That is the second thing. Now, the third thing is with respect to FU by FI ratio. Now, if you look at this particular two graphs, the FU by FI ratio in this particular graph is quite high, right? The FU is 500, the FI is 250. Here it is less. FU is 500 and FI is 400. So there is a large gap between the FU by FI ratio. So we know that if I look at a cantilever beam and I increase the P load value at the end of the beam, I get yielding of the member current quickly at the very end of this member, right? So if I have a larger FU by FI ratio, by the time this guy yields and then further this one yields, there is enough strength on the behind member to reach to a 500 value, which means if I have yielding starting here, then because my FU by FI ratio is high, there is a greater potential for larger length of the member to undergo yielding if my FU by FI ratio is more, which means by the time this guy reached 500 here, a lot of the section would have gone into yielding. Whereas if you look at this part, let's say this has reached yielding first of all, and then the force is being increased. This Pmax is getting increased more and more. So as soon as I reach this length, this end would have already reached 500 MPa, the peak load. It can't go more, which means if I have higher FU by FI ratio, larger length of my member undergoes yielding, or the plastic hinge formation is made over a larger length, which results in higher rotational capacity in the beam, which is what I want during an earthquake, right? You want higher rotational capacity. If you remember section 12 of IS 800/2007, it says, I want the peak strength in a beam column joint or a moment resisting frame. I want a strength to be adequate enough up to 0.04 radians of rotation. So if I have less amount of FU by FI, I will reach the plastic hinge over a small length, And after that, there will be some kind of inelastic buckling or non-linearity or instability coming into the member, which I'll show later. So the crux is, if I have higher Fu by Fi ratio, I have larger plastic hinge forming in my member, resulting in larger rotational capacity. Now, as I said, these are all the criteria that is needed for the member. Now, you will say, sir, with respect to the members or the buildings that were built earlier on, we have been using E250 or mild steel as the main grade of our structural systems. But understand that there was from 2012, there was an amendment to IS 800, wherein it was also mentioned that earlier, you can see the earlier IS 800 2007, before 2012 amendment, that bracing member shall be made of E250B, special moment resisting frame shall be made with E250B. But when you see this amendment, it says bracing member shall be made with E250B steel of IS 2062 or of steel having Charpy value V notch energy greater than 27 joules, which means in 2012 itself, our engineers were given a license to migrate to E350 grade also. That is the crux that we have to understand. There was already a license given to the engineers to go to E350. With this particular code, now it's closed forever that yes, E350 is currently the maximum grade that you have to use, right? One more issue with the older, the IS 800 code was that it was ignoring the uncertainty factor, which has come in the new code. Now, you understand that when I buy steel from a manufacturer, I get a steel like I say I need E350 grade. Then the manufacturer says, okay, here you are. The minimum expected, minimum nominal yield strength of the material that you're having will be 350 MPa, right? But when I test it in a coupon, you obviously know that the value will not be 350 MPa. It will be 380, it can be 400, it can be 420, right? Now the issue is, if you see here, the uncertainty, this is the mean value of that higher strength that you always get after testing. Let me call it the mean strength of the steel if I test it. So E250, the uncertainty in terms of if I buy a steel of E250 grade, the mean value of the strength that I'm always going to get is to be 250 into 1.4 times. That number will come. That would be the yield strength of the steel that I'm going to get. As the strength of the grade increases, the uncertainty factor decreases. Now, you will ask me, sir, what is the issue? The uncertainty factor, if I buy a steel, like maybe Tata people might be attending sale and Jindal people might be saying that if I'm selling you E250 grade and you're getting higher strength, what is the issue? I'm helping you out. I mean, your member can carry higher load itself. The issue is with respect to, if you think, the example I can give you is strong column, weak beam. Let's say I have designed as per normally a nominal strength only I'm going to design, right? If you remember the strong column weak beam ratio equation, nominal strength only Fi only we were using. So when I have a column and beam, that ratio being calculated based on nominal strength, and suddenly a lot comes in wherein the uncertainty factor in the actual yield strength of the material is high in the beam, there is always a possibility that we might end up with a weak column, strong beam kind of a scenario. So in a seismic kind of a design, this uncertainty factors becomes very important, which means the next question that might pop in your head is, were we doing our strong column weak beam design incorrectly earlier on? The answer would be easily a yes. You are risking. We don't know what is the uncertainty factor, the actual yield strength, we don't know. But as per this code, you will soon see what the code says and how it caters for that uncertainty factor in the strong column weak beam ratio. Now, past earthquake performance, yes, 1906 in US and all, this San Francisco earthquake came in, and whatever structure that you see standing were mostly steel structures. There, the steel was less costly. In India, coking coal, which is used, is imported, and many other factors result in the higher steel cost. That is why people go for RCC. But in US, what had happened is that after 1906 earthquake, people started building steel structures, majorly steel only, because at the end of the day, the seismic performance or the ductility of steel is much more than the RCC structure, right? The cost is a factor that is deciding everything in our country. So we are currently going into RCC and then structural steel in terms of rebar is being used. Rebar is the one which is giving ductility to RCC member, etc. That is coming into picture. Now, in the 1994 earthquake, like they were like, okay, we are building with steel, it is working wonderful, it is like a very good kind of structural steel for earthquake performance, etc. In 1994 earthquake, it was observed that there were failures that were seen in the steel structures. You can see the crack. You can see this is the beam bottom flange. There is an opening here, which is the weld access hole that is given to weld the bottom flange here. There is a weld backing bar given here. This is the column flange. This is the column flange. This is the continuity plate, and this is the stiffener that is given there. So in the most of the cases where in 1994 Northridge earthquake, none of the steel structures actually collapsed, but there was seen a crack that is occurring in the joints area, especially where the backing bar, etc., were being placed. So what was observed was that, okay, what were the reasons for the failure of the structure was they found out that yes, poor welding detail in terms of giving the backing bar, having it in place, not removing it after the welding has been completed is giving as a notch or a stress concentration point for the crack to develop. The second was another, they were using A36 grade of steel, which as I explained before was resulting in most cases like strong beam and weak column. So they came up with A992 grade of steel currently being used in US market, which has an uncertainty factor of 1.1. But if you look the code AIC 360 or 341, you will find that the A36 grade, which was used during Northridge earthquake, was of a higher uncertainty factor, right? And what the final outcome of this particular Northridge earthquake was that they came up with the code of AIC 358, which is the code that is currently used by many of us in India with respect to the pre-qualified connection, the connections which has been rigorously tested and the procedure has been given, which we follow to use in our steel design is what is this code, which is the most important code right now, which has a lot of pre-qualified connection given there. Again, one more thing, use those methods, but please understand the uncertainty and the other issues with the Indian material. So don't follow it blindly. That is my thing. But for them, they have their material and they have tested and they have come up with the AIC 358 that we all use. Few of those connections you can see. This is a beam column joint. This is a cover a flange plate on top. There is a bottom flange plate. It is welded. It's a moment connection, and it's a bolted web connection that you have there. And when you test it under seismic condition, you get this kind of a failure. Now, it's not a, when you say failure in the sense that it has taken up to the failure load, etc. But you can see a good thing that if you haven't seen plastic hinges in steel structure, this is what a plastic hinge looks like. So during a test, what we do is we whitewash, we put a white paint over it, and you know that when a material yields, it has a permanent deformation set into it, right? Once the material crosses the yield limit, it has a permanent set that comes in. So wherever the white paint has gone off is where a permanent set has already come into the structure, right? And into the member. Now, what you see here at the top, the flanges, you see this is what is a phenomenon known as local buckling. Now, local buckling is inevitable because what happens is when you have an earthquake, this beam is going up and down. There is a permanent deformation that comes in these flange members. And when you have these flange members, elongated flange members going under compression, the inevitable local buckling is bound to happen. So the natural thing to do is how can I delay this local buckling in a member such that, see, local buckling, whenever it happens, you can see when I look at the hysteresis curve or when I look at the deformation, load deformation curve, whenever instability occurs, the energy dissipation capacity drops drastically. So as an engineer, you are like, okay, my rule was strong column, weak beam. The plastic hinges should form in the beams itself. That is forming. But this local buckling is creating a problem for me because it's an instability. So how do I delay it? That is what we do with compactness criteria or the B by T or D by T criteria that we use. So if I look at another connection, let's say I put a stiffener plate on top. What happens then? I've shifted the plastic hinge formation to a further point, but again, you can see the plastic hinge formation here. The member has yielded all throughout the depth of the section. And yet again, you see the local buckling. So local buckling is natural to come in there. This is a reduced beam section. This is also being followed and given in AIC 358 how to go about it. This is like, rather when you don't have this reduced beam section, there is a chance if you don't use these flange plate or stiffener plate, etc., you can have the hinged formation nearer to the column face where your connections are. So unduly stressing the connections is not a good thing. So reduced beam section, concentrate this damage in these reduced. So you're bringing up a location which is weak where you are pushing the plastic hinge to be formed. That is a logic here. So AIC 358 has around 12 connections that is given with respect to design, etc., where you can look about. But please remember, it's your material, Indian steel, if you are using, you have to look at what is the pros and cons of that particular steel. And as I said, compactness criteria that is given in our Indian code with respect to being plastic section, compact section, semi-compact and slender is when you see plastic section, you might say, sir, it is very stringent. I mean, it is the B by T and H by T criteria is so stringent that I'm made to use a thicker section in the flange and web. But please understand that that is being put forward just for the reason that you are not actually removing the cause. I mean, you're not the local buckling is not eradicated completely, but it's actually delayed. That is the thing that this particular B by T ratio is bringing up about with respect to these compactness criteria. So you have to follow them to the T such that you can avoid large deformation in this particular local buckling in the member. So if you look at a brace, let's say a brace, this is the buckling of the brace in compression, then you have yielding in tension. As we said, the green member in the CBF is the brace. A brace also undergoes global buckling. It also undergoes local buckling. So this is local buckling. If you look at in the global geometry, yes, this is the global buckling that you see. But when you look at the local geometry, there is crimping or folding of the plates at the location where the members are bent the most. And wherever that happens, you can see the fracture initiation to start. So global buckling combined with local buckling initiates the process of fracture initiation in a member, and once it initiates, there is suddenly a complete fracture of the brace member. So you have to be, whether it be circular section or hollow square section or hollow rectangular section, local buckling is, this is again local buckling. And you can understand in a square section or a rectangular section, the most stressed region will be the corners, and that is where the fracture initiation will start, and finally it will result in the fracture. So the idea is delay the local buckling to the maximum possible by using of the D by T ratio and D by T ratio. That is what this table is. So you have table 2 in IS 18168, which gives you what is the ratio of B by T and D by T ratio that needs to be used. Now, I would advise all the engineers who are attending here to go to AIC 34116, wherein, or 34122 in that particular sense, that in our current code 18168, the codal committee has put a stringent line that all the members should be plastic, right? But if you look at the international code, it says whichever is the green element. I mean, again, referring to that diagram, whichever is the green, that should be the most ductile, and whichever is the black can be a moderately ductile member. So the equivalent table in AIC 341 has one more row which says the highly ductile member के लिए what is the B by T ratio, and for a moderately ductile member what should be B by T ratio. So if you read the code closely and if you understand the procedure, currently we are worrying in terms of ki maybe the engineers won't understand. So it's always safer to go for all sections to be plastic. It is okay if you go for, if you understand theory well, you have nuances or you have conditions there in the code itself that you can change your design accordingly. So how do you go about thinking about what to do, where to give the plastic section, where to give, you understand that plastic section is the better section in comparison to compact, semi-compact and cylinder, because it can achieve its plastic hinge capacity and can have adequate rotation, which is what you require in a steel member in a high seismic region. So whether it be MRF, whether it be CBF, or whether it be EBF systems, the first thing that you have to understand is what is the ideal behavior. Where are the plastic hinges to be formed? Where do you don't want it to be formed? Where do you don't want it to be concentrated? So as an example, I'm showing that MRF system. You can see the beam ends is where you would expect the plastic hinge to be formed, and at the base of the column. The concept of strong column weak beam was not made for the sense that we are always taught that okay, column fail hota hai to building pura gir jayega. If beam fails, it is like a localized failure. That is not why strong column weak beam has actually come about. The main idea is if you have hinges forming in the beams in a structure, you have more energy locations where your energy dissipation can happen. But if you have it forming only in the columns, it can result into a soft story failure also. With lesser amount of energy being dissipated, you have complete collapse of a structure happening in comparison to all the beam ends to forming the plastic hinges because of the strong column weak beam criteria, resulting in higher energy dissipation. That is the whole deal of this particular thing. So if you have a structural system, whether it's moment resisting frame, EBF or CBF, ideal behavior, what is it? You have to understand first. Then you will come along in the code. This, I'm jumping a few lines here with respect to this, that if you open 18168, it's confusing in a sense that there is a load combination given here which says along with the load combination given in 1893-800, additional load combination to be considered, that is 1.2 dead load plus a factor of live load plus 1 times of ELM, where 1 times of ELM is omega EL earthquake load, which is omega is for overstrength factor. Now, if you have a pen and paper, we are not able to talk more on the codal clauses, etc. But understand that this particular clause, which uses the overstrength, is not for the design of the green members, but these are for the design of the black members or the force controlled elements, right? So you design the green elements for the basic combos that you have already in your code. After that, once you have got the member freeze for the green elements, you use this combo to make the beams or the black elements or the force controlled element to be stronger than the green elements or the deformation control. That is why this is being used. So please understand this codal load combination comes under the global analysis. I'll explain it for the CBF element later on. That this is for the force controlled element only. It should not be used for the design of the green element, right? Those who have come late, black is for green is for the element which is designated for energy dissipation, inelastic energy dissipation, and black element is which we want mostly to remain elastic during an earthquake activity, right? We have not got into the structural system so far, but this is very, very important that you remember SP6, right? But there is one more code that has come in 2004, which many don't realize. But this particular code, IS 18168, is making a mandatory requirement that only doubly symmetric parallel flange standard roll section or built-up section satisfying the compactness criteria of table 2 of 18168 should be used. So you understand that in SP6 we had ISMB 600, ISMB 400, which is like a tape, which had a tapered flange, right? Not a uniform thickness in the flanges. So the issue is if you tighten them with a bolt or anything, you have non-uniform thickness of the members. So in a seismic kind of a behavior, it has a more potential to fail early because of that non-uniform thickness, and the bolt has to be kind of tilted to actually grip it, etc. So the code mandates right now that if you are in a high seismic region 3, 4, and 5, and you are bound to make a structural system like SMRF, SCBF, or EBF, you have to use parallel flange sections. Now, these two have been combined into IS 808. That is the latest revision. That is like now you have both tapered as well as parallel in one code itself. But this code was there from 2004 itself. Many didn't knew about it. So if I ask you what is the maximum depth of roll section available, as per SP6, the number was 600 mm. But as per this 12774 that you see, 12778, that is up to 900 mm. And if I look at the criteria with respect to B by T or plastic section, number of sections are also higher in 12778, and the number of sections that pass the criteria plastic section is also higher in 12778. So you have a larger pool of section that is available in the parallel flange section community. So you can use them in your high seismic region. So it's like mandated now. Don't use tapered flange sections anymore in your seismic buildings, etc. You can go for built up, which is anyway plates having parallel flanges. Now, this is another thing that the manufacturers, if they are already here, or the team from the design team, that this is the section modulus ratio of all the Indian sections that is there, right? And you can see this is for the American sections, the W36, all the W category of sections. And you can see that from the depth of 350 to 500 mm depth, the section modulus available in there, I mean, they have a larger inventory of section with this particular depth. Is how it is achieved is, if you have a 500 mm depth, how do you achieve larger section modulus is through increased thickness of the flange and the web. So if you are a manufacturer, if you can give me a larger thickness rolled eye sections, etc., the advantage as an architect or a designer is that if the architect makes a box of 400 mm by 400 mm, I would have in my inventory the section sizes that will allow me to put a particular member with respect to that particular size. So the advantage is the architect will never be worried कि sir ये तो 600 में pass नहीं हो रहा, I need a 1 meter depth column to pass the requirement or a beam of that requirement. So that advantage they are having, we should be also moving into that direction itself, right? So now coming directly to moment resisting frame. So we are starting moment resisting frame. Simple, the first moment resisting frame, steel moment resisting frame was the Chicago building, home insurance building in 1884. At that time, you can see what is the connection that is there between beam and column. It is very rigid. You have lot of connection members, etc. The Empire Steel building started using rolled eye section. These were mostly built up section back then. Then post World War, they realized that, okay, we need to be optimizing the connection design, etc. And then they came up with the kind of connection that we see today, right? And a lot of testing in 1960s and 17, a lot of testing has happened, wherein, they have checked what is the connection behavior, etc. But the mistake that they did is they were all smaller sections. They were not actually the large sections that we're using in building, which is also one of the reasons that detailing criteria, the welding quality, the Charpy value of the welded. See, when I say 27 joules in terms of the base metal, if you look at 18168, requirement for the minimum Charpy for the weld is also now given. It's higher value, 48 joules or something like that, because you know that you are not depending upon the ductility or percentage elongation in a weld, right? Weld is the most strongest member. So if I look at moment resisting frame and I ask you which is the most strongest element that you want in your strongest member you want, you would always say connections. Then you would say, okay, columns, then panel zone, then beam. Whereas ductility wise, you will go in the reverse order. Beam should have the highest ductility, panel zone the next, then the column, and the least ductility you would want. I mean, you would always want your weld to be the strongest or your connection to be the strongest. So in that sense, the higher Charpy energy is given for requirement for the minimum energy in welded connections. So since they did not test the larger sections, etc., they went up with these failures, etc., which resulted in AIC 358, etc. Right? So in a moment resisting frame, the ideal behavior, it comes once again. This is the ideal behavior that we want plastic hinges to form at the ends of the beams, at the bottom of the columns, etc. Inelastic behavior is accompanied by local buckling of the beam and column flanges and large deformation in webs. The idea is to limit the deformation that comes from this instability, not let it proliferate by the use of compactness criteria. That is the idea of compactness criteria. But in a moment resisting frame, even if you do limit state method, when you, in terms of strength, when you look at all the combinations, etc., and you start your design, strength criteria is easily achieved, but the things that push your value of your section sizes is mainly dependent upon the drift criteria, because yes, moment resisting frame does not have much of a stiffness because of vertical and horizontal members only. There is no diagonal member which is increasing the stiffness like in a braces. Then there is P delta instability. You have to take care of the P delta ratio. Then strong column weak beam criteria you have to satisfy. Earlier in IS 800 it was 1.2. Now there is a problem that it is 1.4 right now in the new code. We'll come to that soon. And if you have sorted that also, then the compactness criteria comes in, so that you have a highly ductile member. The code says make beams as well as columns to be plastic member, nothing to be other than plastic member. As I said, you can, as a designer, if you know the code, you can go for a lower size, but these are the things that bumps up whatever you need as the requirement. And then finally, when you have come up with this is the section modulus or this is the cross sectional area that I need, you check up the list of sections that you, suddenly you don't find the appropriate cross section. So these are the things that are there which bumps up the final cross section that you apply in your system, right? But ductile behavior in a high seismic region, you need ductile behavior. So compactness criteria is required. Frame should be laterally braced for stability. Even the region which is the plastic hinges getting formed, you need that location to be braced so that it does not undergo any lateral movement or anything. Then strong column weak beam philosophy, we have already talked about that. Then designated protected zone is said, right? What is a protected zone is where those plastic hinge, you have seen that paint getting removed, right? At that location where the plastic hinge is expected to be formed is called as a protected zone. And that zone has to be protected at all times, that nobody should weld any secondary member or should not poke a hole into it, or nothing should come or into that particular location. It is sacrosanct that that particular location where the plastic hinge is to be formed is to be protected at all cost. And whatever weld comes in that plastic hinge region, which you understand that due to plastic hinge formation the weld will be too much stressed at that location, that particular weld is called as a demand critical weld. So there you have to take care about what is a minimum Charpy value, or the welding has to be done properly. That is that demand critical, that weld that we are talking about. And then the panel zone. See, and the panel zone is what comes up next. I'll quickly cover that also. Saying that the panel zone, there is a confusion that whether the panel zone, which is the junction between the beam and column, that location, whether it should yield or not. The answer is it should have limited yielding, in a sense that if there is no yielding in the panel zone, the onus of energy dissipation falls rightly on the beam only. and that has resulted in experimental studies of the earlier failure of the beam. But if you have some limited yielding in the plastic hinge region or the panel zone region, then it aids in reducing the stresses that is developed in the beam. So you have a sharing pattern. So alone you are good, okay, but if you are together in a battle, it is better in the overall performance. It lives longer. That is the whole aspect here. Now, one mistake that I've always seen with respect to engineers that they do is, if I'm using an I section, you have to be very careful here that the I section, this is in the plan, right? You have I section, I've shown like H, the alphabet H like here. The beams normally, let's say I'm taking I section itself. It's an I section connecting to the columns, etc. So if my I section is providing a moment about the major axis of the column, and the major axis of the column is oriented in this direction itself, I can call this as a moment connection. I can make it as a moment connection. But if my beam is getting connected to the minor axis of the column, then in your ETABS model, even if you give a rigid joint, etc., it is not going to work because the column is incapable of providing that much amount of restraint. So giving a release here and providing a shear connection would be the most ideal way of going about. I'll repeat, if you're, see, beam being bent about the major axis is fine, but column being bent about the major axis is the major say here, that if my column is able to restrain the beam and is able to transfer the moment from the beam to the column, it can be done only if the column is oriented in the right direction. If I connect my beam to the minor axis of the column, that means if I connect my beam to the web of the column, the web is very thin, right? And I'm connecting the major axis, the moment from the beam will be transferring to the minor axis of the column. And if it is weak enough, it will not be able to act like a rigid beam connection, right? So don't do that. Go for a moment release and connect it by shear connection. So not all frames, the earlier what I said, not all frames need to be moment connections. In US, what they do is the peripheral frame is what the moment connections are. You have moment resisting frame on the periphery, with sometimes this corner column being a box column or a cruciform, and rest internal frames are all gravity. It's designed for gravity, but for deformation compatibility. So when the earthquake comes, the due to higher stiffness of the peripheral members, the forces will flow there. Some amount will come inside, let's say, but due to the seismic forces, this will deform a bit, right? So that deformation compatibility, that due to rigid frame, these guys will also move alongside with this. These gravity columns, etc., will move alongside with it. You have to cater for that deformation compatibility a lot. Otherwise, you're designing for the gravity forces only. The second thing is, okay, if you have a beam, this is like a beam subjected to, I mean, the cross section is given here at different levels, and you have equal moment acting at both ends. And if that is the case, if I apply that load, there is a lateral torsional buckling that happens. You can see the blue cross section of the beam twisting and turning at this location. In the central portion, you can see the twisted one. If I support it at the middle only, if I somehow have some magic wand in my hand and I support it at the middle only without controlling the top and bottom, I will get heavy rotation, or I am not able to support the lateral torsional buckling that I was seeing. But if I somehow connect the top and bottom flange, then I'm able to restrain the rotation in the beam due to that particular forces that I'm applying. So there will be no lateral torsional buckling or anything if I support the top and bottom flange, right? So accordingly, you understand why lateral torsional buckling happens. And in a seismic case, there is a possibility that, okay, reversal of stresses can also happen. So in that case, you have to hold top and bottom. And if you read the current code, it says the IS 18168 when to hold the top cord, top flange, when to hold both the top and bottom flange. Like this image here, this is the main beam, and you are holding the top flange and bottom flange by this. And you are having from the secondary beam, you are having additional attachment or this thing which is having this connection to it. So lateral bracing, as I said earlier, lateral bracing of the beams and columns is necessary to achieve the maximum ductility in the member. Now, splice of the section, yes. Earlier, there was no mention of where to give the splice. We normally had the notion that, yes, it is better to give in the middle, but architect would make us run around and around saying that, yeah, at the middle of the column, it is not looking good. Shift it somewhere. So you would say, no, at the joint, it should not be provided. So currently, the code gives a location that it should be at least, preferably middle third, but at least 1 meter away from the beam column moment connection. It is required there, right? That is given there. Now, this is more or less the strong column weak beam ratio. The earlier one, if you see MPC by MPB greater than 1.2, that was there. Currently, the equation looks very complicated right now, but if you look at it closely, let's start with the beam. If I'm looking at strong column weak beam ratio, I need, if I want to be very sure, I need the beam, I want to make the beam to be the strongest and column to be the weakest, and then ensure that its ratio is greater than 1.4, which will ensure that the column is finally strong, right? So if you look at the denominator, you can see Fi into Zp, that is the plastic moment capacity of the beam, right? This equation is simple. Ry is the uncertainty factor. So it says, okay, the material has the capacity, or the beam can have a higher capacity than what is the nominal plastic moment capacity of the section. This Ry is the uncertainty factor, and 1.1 is the strain hardening ratio, right? So now you understand that whatever can increase in the beam, I have now included in my equation. It's not looking simply as an MPB. But when you look at the column, I have again the plastic moment capacity of the column, but this 1 minus Pu by Pd takes care of the reduction in the moment capacity of the column due to axial force coming into it. So now you understand what I initially said, that I am taking whatever maximum load can come in a beam, and I am taking whatever the reduction in moment capacity can happen in a column. Then I am making that ratio to be greater than 1.4 MPC by MBO. In that sense, then finally, when I've taken up all uncertainties, I've taken up all the capacities that can come. And then if I do, I am very much sure that whatever image that you've seen earlier with respect to yielding of the beam, etc., I'll achieve it. That is the beauty of the new code, that it assures everything, right? Panel zone, yes, we have discussed already that panel zone, limited yielding in the panel zone is good. Any problem with this? Yes, in the plastic hinge region, this is a reduced beam section. In that, somebody has kept the flooring welding has been done here. So in the protected zone, somebody has done something wrong. This is not at all viable as per the new code. It should not be done, because you are damaging the potential of your hero, who is the nonlinear energy dissipating element here. Now this is an end plate. What do you see? This is a moment connection. I think it'll take 15 more minutes. This is a moment connection here, or even more in terms of making you understand. Moment connection, this is a simple shear connection. If we had time, we would have discussed this. This is the CJP welding. So this is where the splice connection is being given. CJP is complete joint penetration weld, a butt weld that is given by chamfering the plate, etc., so that you get a rigid joint from there. So that is all about this particular aspect. In concentrically braced frame, moving on to concentrically braced frame, it is a different concept. See, in your house, the same concept, I'll answer it. In your house, you have electrical appliances, and then there is a fuse in your this thing. When there is a voltage increase, the fuse blows off, and your main appliances, electrical appliances, get saved, right? The same is the concept with the brace element. As you remember, the brace in a CBF system are the green elements, or the deformation control elements, or the elements which are responsible for the energy dissipation, right? So when an earthquake comes, let's say the earthquake comes, the ground moves from left to right, the building, this one, sways from right to left. So this particular brace will be in tension, no issue. The hysteresis curve shows that the member, when yielding in tension, dissipates a higher amount of energy. But when the ground moves from right to left and the building sways from left to right, you have compression in these members, right? So buckling will happen. And whenever we say buckling in steel, we are scared that it should not happen. Buckling is not at all required, etc. But understand that in a brace frame system, a brace that is given, buckling is part and parcel of the whole process. You can see that it has to buckle, it will buckle, but the energy dissipated in the compression side is much lower than what you have in the tension side. So you have an asymmetry in the energy dissipation. You don't have symmetry kind of behavior. When, if you remember, the hysteresis curve in beam column joint in a steel is like a symmetrical hysteresis curve. You have an asymmetry here. So the solution is, a brace element in a CBF cannot be given as only a single guy. It should have a brother standing side by side to it. So at a particular floor, there should be two braces, that when one goes into tension and other goes into compression. When there is a reversal of load, the other one goes into tension and the first one which had yielded goes into compression or buckling phase, right? So that is the thing. So energy dissipation happens in a CBF system through yielding in the brace and through buckling of the braces. buckling, even though it yields lesser amount of energy dissipation. You can understand if I'm using a brace of a higher slenderness ratio, my energy dissipation capacity will be much lower because it buckles much earlier, right? But if I have a stout and a compact section, both motor section, if I'm using, my compression capacity will be high. So the buckling load, initial buckling load will be very high, and I'll have some amount of energy dissipation at the lower end. So this is the concept. So based on this particular element, I have to design my beams and columns or the force controlled element that will come to it, right? So this I've ensured what is required in a brace frame system. Is there anything different between ordinary concentrically braced frame and special concentric brace frame? No, the concept is the same, the energy dissipation is the same, but detailing, since SCBF is given in high seismic region, it will have higher deformation requirement. The detailing has to be done properly. That is why that is a difference coming in OCBF and SCBF. So undesired performance is connection failure, column buckling. No, the force control element in that column buckling and all should not happen. The beam failure should not happen, and the column tension. Since you give braces in a single, what do you say, bay, there is a higher concentration of tension and compression forces in the column. So there is a possibility that either the column can buckle or the tension of the column can cause failure in the connection. So these should not happen. What is desired, if you look, brace buckling is desired, brace tension yielding is desired, column flexure is desired, and beam flexure is desired, right? Now, the important criteria, if you're a designer and you're deciding upon what is the important things to be decided for a brace frame, the slenderness ratio is one big deal, in terms of which there is a limit given in code with respect to slenderness should not exceed 162 or 165. The meaning is if I go more than 165, it is more like a rope. Like it will have yielding in tension, it is good, but compression, it does not give me anything. The asymmetricity in the hysteresis is very high. So better have some amount of this thing. So the code says, okay, keep it below 165. Then compactness ratio, as I said and shown with the images earlier, if my compactness ratio is good, the fracture initiation is delayed in the member, which means my brace will survive. Now, the hero in my story in CBF are the braces. The more they survive, the more they will dissipate the energy. And cross-sectional shape, you have seen that in the hollow rectangular and square shape, the corners are fracturing early, right? Because of the stress concentration. So you might have seen industrial buildings or metro stations with hollow, square and rectangular members. That is okay as long as it is resisting wind. If wind is your governing design, hollow rectangular and square is fine. But if seismic is governing your case and you are designing a CBF or an SCBF, hollow circular is a better choice than the hollow rectangular or square. Or even better if you can go for an open section like an I section. Channel and angle sections are not good enough because of the asymmetry of the cross section and the other problems that are there. So if you can, I section is more preferred, then circular section, and then hollow, square or tube. 18168 mein circular section is not currently provided there, just for the sake that if you cut a slot in the gusset plate, the connection I'm not covering here, but the getting a concentric connection in a circular section is a bit difficult. That is the issue why they have not put it there. But as I said, if you have the knowledge and if you have the capability, go for a circular section. So coming to CBF system, what is ideal behavior? Where do you want the hinges to form or the plastic hinge? The most ideal will be at the center of the brace. Then at the ends of the gusset plate, where gusset plate outer plane stiffness is very less, right? So you can have yielding in the braces there. And then you can have at the base of the column. You can see here, I've given it as a solo CBF system by drawing the image as a shear connection between the beam and the column. So that's why the next thing comes here. And finally, the failure mechanism happens by the yielding in the center of the beam. Right? This is the way in which the plastic hinge should form. Any other way would not be ideal. Right? Then, as I said, global buckling happens very initially, 0.3% drift or a very less amount of axial deformation, it happens. Then it takes some cycles. So if your compactness ratio is very high, so then if your compactness is very high, means it's a very sturdy, stout section. Your local buckling happens much delayed way, which is what we want. So after a number of cycles, the local buckling happens. And once local buckling happens, you can see the very next cycle itself, the fracture initiation starts. And as soon as the fracture initiation starts, it fails. So these are all the issues why the current codal committee, due to asymmetric behavior of the braces, due to in a certain floor, if the brace yields or buckles, suddenly the stiffness decreases and there is a tendency for soft story to form. That is the reason why the code has removed it from zone 5, in terms of it is not a good, I mean, a better performing structural system than MRF or EBF. You should avoid it, right? So then this we have already answered. The I section is better, then hollow circular, and then go for a square, right? So now I want to take you through the procedure. I mean, this procedure in concept wise you can use for EBF systems also, right? So if I have a building, if I have a steel structural system, let's say in your mind you think of a rectangular structural system, and the first thing would be where would you want to place your braces, right? The easiest choice would be, yes, where you were placing your shear walls, let's say lift core or staircase wall and all, you can provide your braces. The easier one would be, since I need some kind of torsional rigidity, if I want, I'll place it more towards the farther end of the building, outer end of the building. So external, the frames, the outer frames is where I would normally provide my braces, let's say. Now there are certain configurations that the code allows. Let's say I will come to that particular configuration, but let's say it allows a certain configuration. The way I put the braces, if it is a single story X, if it is a chevron or split X, I have to choose what is the configuration. The analysis procedure, you can go with equivalent lateral force method or response spectrum method or time history method, any which one you can choose. And what you do first of all is you find out the base shear, right? As a normal procedure, you find out the base shear by, let's say, I'm giving an example, go for response spectrum method, mostly the higher dynamic method, because it takes care of any mode shapes or anything like that. So I'll explain to you in time. Let's say I've calculated the base shear in the building and I've distributed the base shear along the height of the building, let's say. So the first element that I would design with respect to the distributed forces, the combo that I've used is what is given in 1893 and IS 800, whatever load combination, 1.5 dead load, 1.5 live load, 1.2 earthquake, whatever is combination is there, because minimum you need that much amount of strength for the demand, seismic demand you have, right? So whatever that force comes, the first element that you design, where your brace and frame, everything is given, is the brace that you start with. So the most ductile element or the deformation control element in MRF, CBF and EBF is where you start your design. So let's say you get the force flow into it, you get tension, you get compression, and you design your braces, right? Mostly in CBF system, the compression member governs the design. So there will be a buckling load that comes in, you design for it, and mostly whatever cross section comes naturally covers whatever tension demand that is coming in the member. Once you have decided what is the cross section, let's say you have chosen I section or a circular section, the next procedure which satisfies that particular force demand, next thing you do is check the slenderness limit as well as the compactness criteria. So let's say you've checked everything. So 1000 kilonewton is the force demand. You designed a brace to carry 1200 kilonewton, let's say, after checking all compactness and slenderness criteria. Now the next step is to design the beams and columns in the brace frame system. So what will you design for? The capacity design says whatever maximum force your brace can give to your force control element, designed for that, right? The maximum worst case. So my demand was only 1000 in the brace. After designing, due to higher section and everything, I give the capacity of the section is 1200. So whatever that 1200 section is going to give is what I will apply to my beam column element, beam and column. That is a force control element. So there is two types of analysis. One is the global analysis, which is what the earlier clause that I had showed you, right? So your braces is there, the frame is there, your lateral forces are applied, that is a distributed lateral force. You use this combo. You use the overstrength for SCBF, which is 2.5. So what it means, let's say you have designed your brace for a combo of 1.5 dead load plus 1.5 earthquake code, let's say. Now I'm using a factor of 2.5 to design my beams and columns, which means naturally I'm making it stronger than the braces, right? That is what I call as a global analysis. The next is I have to check the local also. There's a local analysis in CBF. It's a bit complicated because earlier this was not there. In the previous version of codes that you check, there is not previous version of American code. If you see, it was not there. What it covers here is that there will be an instance in the life of the CBF system where your tension will be maximum and your compression will be maximum initially when the loads are in a certain state. But once the brace buckles, there is only a limited amount of strength that remains in the compression. this thing, right? You remember, once it buckles, there is only a steady value of compression that it can have. It gradually reduces, but the code has reduced, limited it to a value of 0.2 Cmax. So this is Tmax. Tmax is what is the maximum tension that can come in the brace. So Fi into Ag, you can see here yield strength in the gross cross-section area. But don't forget the uncertainty factor. You have used a E250 grade brace or a 350 grade brace, the actual yield strength might be 300 MPa. So that is what this tension capacity gives you. So you find out Tmax, similarly you find out Cmax. You find out a post-buckle case where the Tmax is still there. The yielding tension doesn't change much, but compression drops down to a lower value, which the code says take it as 0.2 Cmax. And in this state, how do you do this? The code says remove all the braces. Earlier case, in the global analysis, the braces are all there. You're finding out the forces in a normal case itself. For local analysis, you have to remove the braces, keep it as a moment frame or a shear kind of a cantilever column with shear if it is a solo CBF system. And then in the place of the brace, you provide what is a Tmax and Cmax as a force resultant. So you will resolve the forces. The horizontal component of Tmax and Cmax will come as the horizontal force here, and whatever the vertical component will come here. So in the end, what you will have, once you have frozen the brace design earlier on, you will not going to touch whatever the case may be. So in the global analysis also, if your brace fails in the 2.5 over strength, you are not going to change it anymore. That will remain as it is, because you are designing for 2.5 times the beams and columns so that it stays stronger than the braces. That is the concept. So when you do this local analysis, there are no braces. So you're aiming directly for the beams and column design. So for these combo, you design for the whatever worst case that can come in this thing. Why this came about, you may ask here, itna complicated, why to make it? Is because after Kobe earthquake and Northridge earthquake, they found that wherever the chevron configuration has come, in that location, they were designing as per this global analysis only they were using. So that was not able to catch this undue excess vertical force that comes in the post buckle case. So when you resolve, if you have a calculator, everything, you can check now itself that the vertical component in the post buckle case is much higher than what it is in the pre buckled or the global analysis case. So such a failure, when it was seen, it was understood that specifically in terms of chevron configuration, there is a condition that high axial force may come due after the buckling of the brace. So that has to be protected. That is why this local analysis has come about. Now, as I said, there are certain configuration that is allowed. These are the allowed configuration that can be used in SCBF. Whereas these configuration, because there is an extra additional force coming in the column, it is not allowed. There is like knee braces are coming again, undue forces will flow into the columns. It may damage the columns. It is not permitted to be used in high seismic region. And single braces, it's a strict no. Anyway, you can have one more bay here with one more brace here, then you can use it. There is no issue with respect to that. So single diagonal brace frames are not allowed. This is split X, this is single story X, this is the chevron configuration or the inverted V. Inverted V is where that local analysis has taken up shape in terms of the imbalance in vertical forces, and that results in the failure that is shown in the pic here, right? Coming to the final EBF link. Now here is one more concept that comes into picture. EBF link, as I said in the initial thing, it is a green short link, which is the most energy dissipating element. In this, the brace is not allowed to buckle or yield, right? It's a force controlled element. So it's like it should remain mostly plastic, and then moment can also be transferred. Without the gusset plate also, you can directly connect it to the edge of the link element. But the energy dissipation is done by the small link element. So my question to you guys is, if the link element is very small, what will dominate if you think in your mind? And if the link element is more, how will it yield in non-linearity? I'll complete, Praveen. In 10 minutes, I'll finish.
No problem. Please continue.
Yeah. So the link element length is the most important characteristic here. So if you look at a link element, let's say I have an eccentrically braced frame. This is linked to column kind of an eccentrically braced system. This is linked to beam kind of an eccentrically braced system. And this is what the code actually suggests to use. IR 18168 rightly tells the engineers that choose this kind of a system, not the link to column, because of the fact that link is our hero. It undergoes non-linearity, etc., and it is transferring that non-linearity to the column, or deformations and too many things happen at this location can damage the column. So it is better to have all these things happen in the beam itself. So for that reason only the code says use this kind of a configuration. Now, if you look at this configuration closely and this graph, it says relative frame stiffness and E by L. E is the link length and L is this particular dimension, or you can say E can be this length and the total bay width, etc. So when I have the link much closer, my stiffness, if my E by L is very small, means this gap is very small, my stiffness is much higher. If it is E is 0, it is a CBF system. And if E is equal to L, then it is a moment resisting frame system. Understand? So as the link length increases, my stiffness decreases and reaches to the MRF level. And if my link length is small, I have higher stiffness in the system. There can be many variations in the link element. You can have this eccentricity, this kind of configuration. This is the link element here. This is getting popular right now in terms of vertical link element, as in the case that people are devising certain link element which can be removed after earthquake, as link in the beam will get damaged and it is very difficult to remove. But if it is something which is external, you can actually remove it and replace it. So during an earthquake, the link is the element that undergoes non-linearity. There is no buckling or anything right now that is there in the brace or anything. It is just the yielding of this particular member, right? Now, if it is this thing, you can simply understand that if such a kind of deformation happens, the slab is bound to have some cracks or something to be developed, right? There are certain clauses that are given. I'll come to it later on. I mean, in terms of a different session maybe. But this is how it looks like. This is an EBF system in this particular building. This is a older building in link to column connection that is there. Strictly, this is not allowed as per the current Indian code 18168. This is fine as per 18168. So you can see, you may say, sir, link element though, this is the link element that you said, but you have stiffness and also, isn't it a protected zone? Like in a CBF system, the brace are the green element. Those are the protected zone. Nobody should pierce or anything, do anything like that. Similarly, in a EBF system, this is a protected element. Why are stiffness given? Aren't they kind of intruding upon that protected kind of a thing? We'll come to it soon. So a link element, how will it perform? If it is a if it is of a very short length, you know that the shear force will be very high, and then you are bound to get shear yielding in the element, right? Shear yielding in an ideal short link element, there will be yielding in shear, a pure shear case that we normally think. And then if the deformation continues to happen for a long time, then shear buckling due to shear forces. As you see in a plate girder, like tension stiffening effect and the compression gets buckled, the same phenomena will happen in terms of a short shear link. Whereas in a long shear link, if flexure dominates, then the flexural hinges will form as in the case of a beam in a moment resisting frame, only in the ends. So you understand that when in RCC, the shear is a very feared upon thing, as in the case that shear is brittle, the behavior of a RCC element is very brittle in shear. On the contrary, in case of an EBF system, the smaller the shear link is, I mean, shorter the link element is, and the behavior is shear dominated, the better its performance is. The higher energies dissipated based on short shear link rather than a long shear link. So the code has come up with a certain equation that if the link length is less than 1.6 plastic moment capacity by plastic shear capacity, it will behave as a pure shear kind of a way. And if its link length is more than 2.6 times MP by VP, then it will be pure flexure kind of a behavior you will get. So designers have this guidance, whatever cross section that they are using, if they follow this criteria, they will either land up with pure shear or pure flexure. If they fall in between, it will be an intermediate behavior, right? This is the codal clause. So as I said, short shear link is much better. Now, if I show this image to you and ask you, these are all three links here, short, intermediate, and flexure, you should be able to understand based on what I already said. If I paint it before the experiment, and I say that if there is some permanent set deformation or anything that happens in the element, there will be a flaking of the whitewash or this paint that I have given. So in terms of the first element, you can see the flanges are intact. The white paint that is there is intact. The web only has dissipated all the paint that is there. So this is where the shear yielding has happened. This is the short shear link. In case of this element, you can see nothing happened to the web, nothing happened to the flange except for the end location, which means this is a flexure type of a link element. In this case, if you see the web panel, all the paint have gone off, and towards the end there is local, I mean there is no paint here, no paint on the flanges also, no paint here, no paint here, and there is local buckling of the flanges here. So this is an intermediate case where you have shear and flexure coming into picture. But among the three, this is the most stable, more energy dissipating element in terms of the link length. So link length, shorter the link length, the better the performance would be. Now in a link length, you can see the tension stiffening effect and the buckling in compression. This is a plate under the link, which is small in size under pure shear. There is buckling in the compression phase and tension this is compression this way, tension this way. So if you provide stiffness, look at the difference in the hysteresis curve. So if I have stiffener here, each of the individual panel will now act like a shear panel. Buckling will happen in those individual panel. The buckling capacity, if comparison to left, here it will be more because its effective length has reduced. So that causes higher energy dissipation in the stiffened link element. That's why you see stiffness in a link element, right? So as the link length reduces, energy dissipation capacity increases. That is the whole deal. Now, if I ask you about the design, how do you do the design? Think the same way as you did the design for CBF. You have a EBF system for whatever forces that is there, for the combination of forces, you design the link element first, and whatever is the peak capacity of the link, based on that you design your beam, column and braces based on that combo global analysis. There is no local analysis or post buckling analysis in case of an EBF. It's straightforward. And then once you have found out the forces, you can use a column tree like this. There are some rollers missing at these levels which will give it stability, otherwise with these forces it's going to fall down. So if you do the proper analysis, then you'll find out the forces in the force controlled element, and accordingly you will be able to design these members. So this is the whole combo of with respect to the concept of using IS 18168. Further on, I constantly do these courses again. On 5th of December, there is one more course by Instack where we go more into the clause by clause of what the clause says, what is its meaning. Here I have only tried, there are students here, so more of in terms of understanding what the structural systems are. And I hope with this lecture, you get attracted more to steel structures. It is more ductile, it is more better in terms of high seismic kind of a requirement in comparison to RCC or masonry, which in terms of steel, it is much better. And I would encourage that some fear should go off in terms of that. So if you have any doubts or anything, you can ask now, or you can also mail me after this session is over. Back to you, Praveen.
Yeah. Thank you, sir. Thank you so much for the insightful lecture on the steel design, and also covering some of the seismic provisions of IS 18168-2023. So I must say that your clarity, the depth of knowledge and the practical examples made this topic truly engaging and easy to grasp. So thank you so much. So over to Vikas.
Thank you, Praveen.
Thank you, sir, for the insightful. Now we'll take the questions from the participants.
Yeah.
Okay. Sir, if okay, we have many questions, so
Okay.
I'll go one by one in brief. There is a question from Mr. Ravi Kiran. He's asking if FU by FY ratio is very high, then what is the overstrength value to be used in the capacity design?
No, the question is very valid in the sense that currently FU by FI ratio in the capacity design, see, FU by FI ratio is more with respect to what is the maximum capacity a particular element can achieve, right? So if I have a E250 member and its ultimate capacity is much, much higher, then the maximum force that can get transmitted from the member, the deformation control member to the force control member, will be much higher. So yes, the question is valid in the sense that what is the background of giving 2.5 or 3.5? The better idea for the engineer should be that even if they use 3.5, they should always keep a close look on what is the peak force that the deformation control can give to the force control element, and accordingly modify what is the, you can do a local analysis. I mean, whatever that combo with overstrength gives is actually a global analysis. It is easy for your eyes and your ETABS or STAT software to kind of put in as a combination. But if you have the mill test report and from the beginning itself, you know that no, this particular grade of steel, somehow its uncertainty factor, if you see, it is not just in RY, it's also in RU also. So whether it exceeds your particular limit and it can apply more forces to the force control element, you should do the modification. The code is just a minimal document guideline. So you should focus upon the mill test report or do your test with the material that you have. Yeah.
Thank you. The next question is, the use of T sections is a general practice for braces. So IS 18168 does not specify anything about it. Does that mean its use is not permitted now?
No, actually, if you think of it, as I said, if your wind is governing your design, go for it. Go for channel, angle, anything you want, because you understand how it's going to behave, its slenderness ratio, the capacity, everything you understand. But when you look at seismic kind of criteria, you need a stable energy dissipating element. Your hero in a brace frame is your brace. So if you use an element which is unstable, or instability is going to come into the play, that it will not achieve its overall strength because of, let's say, torsional buckling or any other factor that is going to reduce the length. Why do you want to use a T section whose capacity is going to be less in a place where you need more energy dissipation from a particular member? So ideally, nobody is stopping you from anything. As I said, circular member is not mentioned in 18168. But if you look at outer American code, it is given there because of the advantage. So look at the codal clauses, etc. T angle, those are very weak members in terms of compression capacity. Compression, even though less, it's still significant. That is why the code says use less than slenderness less than 165. So make use of what you have in terms of energy dissipation. One more thing to say, the code currently says EBF should be used in zone 5, 4 only, and this should be relegated to a lower seismic category CBF. If you look at outer code, foreign codes, SCBF is allowed to be used in high seismic region also.
Right.
Problem
There is
is
a question also related to that, so we'll cover at a later stage.
yeah.
So there is a point from Mr. Ballas who is asking, the slenderness of 75 is mentioned in IS 18168. Can you please elaborate where at all to use it, the slenderness of 75?
Slenderness of 75, I am not sure. If it is with respect to braces, the limit is 165. The peak
165.
limit limit is 165. It is given in the code. It's given in IS 800 also in terms of the similar number. The next part of the question is,
So they are referring to this clause 7.2, which says limits the slenderness of columns to 75.
So basically, if you have a slender column, I mean, it's about lateral bracing the column. So it's more about when you have braces, when you have beams and columns, the braces itself, it will not perform very well if your slenderness of your column is high. As I said, in a braced bay, due to the braces attracting more forces, you have large compression and tension forces coming in the columns.
So let me clarify more on this.
Yeah.
It says clause 7.2 limits these column slenderness to 75, whereas clause 121.4.2 says to design the columns as per clause 7 of MRF systems. By this, we need to limit the slenderness to 75 for moment resisting frames. But similar statement, that is design the columns as per clause 7, was missed in SCBF clause 12.2. Does it mean that the given slenderness limit of 75 does not apply to SCBF systems?
You have to understand few things. First of all, when you say SCBF system, it is not a braces being put in a moment resisting frame.
Right.
Then it becomes a dual system. Then it is no more a CBF system. So a CBF system is where you have a brace and where your beam is connected through a shear connection. It does not transfer moment to the column. So the column stiffness with respect to whatever the beam is being applied will be much less than what you have in a moment resisting frame where you have a rigidity there. Even though the braces are giving stiffness, individual column slenderness has to be catered for with respect to those connection given there. If it is a dual system, yes, the sharing pattern will come in. You have the stiffness being provided by the braces, and the lateral bracing will be much more stiffer due to the beam attaching to the column. So accordingly, you have to play with the system that you are playing with. So a CBF is not a moment resisting frame with the braces.
Okay. Thank you for clarifying, sir. There is another question which says, can a composite slab, which is a deck slab, be treated as a rigid diaphragm?
See, few things you have to understand. The rigid diaphragm kind of a concept. Yes, we have a codal clause in which the chord rotation is being seen that 1.2 ratio. Check करके we decide upon whether the slab is rigid or not. That comes into play there. Uh, one thing I missed about is key, yes, the deck sheet with respect to its stiffness, etc. When you provide and you look into the whole model with respect to this, you can check whether the rigid diaphragm is not. But the code says one thing that I missed out telling is wherever you have this plastic hinge, let's say the end of the beams in a moment frame or the EBF system, the link element, shear strut should not be given connecting to the slab. You should not go for a composite action at the location of plastic hinge, because once you have a slab on top, the behavior, the hysteresis behavior when it moves up and down will be asymmetric. Like you have a composite slab on top, you have a bottom flange, thin flange at the bottom. So when it undergoes cyclic movement, it will have an asymmetric thing. So I just wanted to clarify that. Deck sheet, stiffness, rigid diaphragm, all that concept goes with the normal what IS 1893 part 1 says with respect to rigid diaphragm and semi-rigid diaphragm. In case of steel structures, wherever the plastic hinge is forming in beams as in moment resisting frame and EBF in the link element, shear strut should not be provided. You're not allowed to take use of the composite action. Yeah.
No, but suppose if the deck slab is properly connected to the steel beams using some kind of a shear studs or the connectors to develop the full composite action. So in such a case, the codes allow this diaphragm rigidity assumption?
Yes. See, at the rest of the location where your secondary beams are supporting the slabs, etc., you are allowed to take use of the composite action through studs. I said only at the locations, the limited locations of the protected zone where the plastic hinge is going to form, there you avoid. That is only.
Clear. The next question says, can buckling restrained BF braced frames be used in zone 5?
Oh, yes. That is a new thing and it will soon come in 18168 also. It is a much better system than concentrically braced frame in a sense that CBF system, you saw what are the disadvantages, that due to buckling, it does not dissipate much energy in one direction. So when you have a buckling restraint braces, what you simply do is you encase the braces by a strong restrainer element. And if you remember the Euler buckling equation, that PCR is pi square EI by L square, that actual equation is n square pi square EI by L square, which we take n as 1 if it buckles in the first mode. What this restrainer does is that once it starts to buckle, and if you have a restrainer, it will not allow it to move in the first mode. It will go into the second mode of buckling. If it is very small, it will go into higher mode. So n becomes 3, 4. So 4 square pi square A by L square. So that strength increases in that way. It buckles, but it is restrained and pushed into higher modes of buckling. That is how the BRB works, and it gives symmetric hysteresis. It's also a very highly ductile EBF equivalent kind of a system, which will be soon coming in. I mean, India, it is getting too late, but it is worthy enough to be used in zone 5 or new codes as per zone 6. Yeah.
So there is a question related to SCBF, special concentrically braced frame. In case of the SCBF, is there any specific requirement that the buckling in the member shall be elastic and it should not happen in out of plane direction? No.
There is no limitation as such. Buckling in out of plane, first of all, buckling in out of plane is not limited in the sense that you have to take care of that once it buckles. The overall deformation will be somewhere from 300 to 400 mm. So don't have any facade elements, don't have any brickwork or anything nearby to it which can get damaged. And then what was the first part of it?
No, it says, is there any requirement that the buckling in the member shall be elastic?
No. You can have normally in a building when you design, the slenderness ratio can range from 40 to 120. That is a range that I have seen it to vary. So it's from elastic buckling to inelastic buckling, it can vary. So there is no issue with respect to that.
This question is something related to practical field. The participant is asking, he's unable to comply with clause 7.4.2. He says practically when you provide the columns on one side of the building, which is carrying the tension, with a less height, more width buildings are rarely constructed in practical scenario. No such clause is found in AISC 341 Is there any
Okay.
workaround for this clause?
I don't have an answer right now for that. I mean, I have not understood the question also very well. So
Because
Praveen,
it's
if you can
actually
send.
in bits, we need to understand what exactly that clause says.
Yeah, what
That's
clause
what
says, I
we're
have to
trying
read it and then I'll get back. I mean, if
Sure,
the
sure.
participant can
No
give
problem.
a mail ID or something, we can write back to them.
Okay, okay.
Yeah.
There is a question which says in a building, if we have SMRF and CBF together, what would be the design procedure and what would be the R factor, response reduction factor?
This question comes around more often in terms of a PB structure, where in the X direction it is more of an MRF system. Whereas in Y direction, the column is oriented in the minor axis. So normally the designer does is that, okay, he takes moment resisting frame, kind of a rigid connection, which, as I said, the column is not sufficient enough to carry that much amount of rotational capability. It's not stiff enough. So in such kind of a system, in Y direction, in a PB structure, X direction is the portal frame, where you have that portal thing, which is a moment frame. In Y direction, a CBF system is more good in terms of it is viable, that it is a solo CBF system. So your beam can be a simply shear connection and you can give braces. The question is again simple. If you look at mode, mode participation, mass participation, etc., and X is independent and Y is independent, your R factor can be 5 and 4 in that sense. 5 in terms of special moment resisting frame, and 4 or 4.5 with respect to the CBF system.
Okay, sir. There is a follow-up question. Can we consider beam to the column web connection as partial fixity for beam with beam rotational spring value as per the European code?
It is how you should design. The person who has written that is saying the right thing, that giving it as moment release is the worst thing you can do. But it helps you. Giving a moment release helps in terms of the deformation, deflection checks, in terms it makes the structure less stiff. So deformations are very high. So your drift check and everything gets checked through that. But the amount of moment that goes into the column through a kind of bolted connection, if the depth of the beam is high, you get all type of, it's not a shear connection, means pin, it's not pin. It's not a pure pin that you give in your this thing. So the spring would be the correct methodology to go for, to assess the forces in the columns. Yeah.
Okay. The next question is, if I have a EBF in one planned direction and SMRF in the other planned direction, what is the value of response reduction factor to be used in the analysis?
Again, the same. I think for EBF and SMRF in our code, it is the same, I think. So there is no difference. In the American code also, EBF is 8 and SMRF is also 8. So the question could have been with respect to the CBF versus EBF, or yeah.
Okay. The next point is why BRBF frames are still not included in Indian Standard Code provisions, although they have been part of design codes of many other countries, at least from last 2 decades.
No, it's coming
why
soon.
Are we? Yeah, this is the first part of the question.
Yeah, it's coming soon.
Yeah, coming soon. Okay. And the second part is, why are we limiting the response reduction factor for SCBF or EBF, although the other codes consider higher R values for these systems?
I would request this person. The question is very valid. When in our country, when we use R equal to 5 for SMRF, the same value of SMRF in American code is 8.
8.
For that, we are both blessed to have that paper by Professor Weissing sir with the Norwegian team. They have compared this particular, they have written a good paper. Professor Yogender Singh sir, with, I don't remember that Norwegian sir's name.
Maybe Dominic Lang?
Dominic Lang. With him, they have written a paper exactly based on this. And when they kind of compare the soil factors, all the other factors included, it comes back to balance only. So, with respect to what value they take, etc., at the end it comes uniform. But the question is very valid. Why shouldn't we take 8?
Thank you, sir. The next point is, we'll try to wrap up within 5 to 10 minutes, sir.
Oh, no issues.
Yeah. With bracing and without bracing, the modal behavior will change. How can we check the strength capacity for frame if the modal behavior is less than the expected?
When they say modal behavior, see, understand one thing, that if it is a moment resisting frame, the ideal behavior, or it's a brace frame, by whichever the case it is, the IS 1893 already says that the primary mode should be translational in the first and second mode. And in that terms, the only change that you're going to see when you have a brace frame is that being stiff, mass participation in the first mode is going to be higher for a brace frame than a moment frame. That is the only change that you're going to see if you design it properly. Rest of the things, the torsion, the third, fourth, fifth mode and all is all different. But there is not much difference in terms of what you see in terms of the mass participate or the modal participation that you're going to see. If it's a 3-story, I mean, in my understanding, more translational behavior or more dominant translational behavior will be there in CBF. But that getting affecting the structure is not. I mean, if it's stiff, it is going to translate more. It will not have that second mode or third mode coming into picture more if it's a 3-story building. Mass participation will be high for a CBF. I don't see a much difference between the two in terms of any other way.
Okay, sir. Thank you. If there are only crossed braces, X braces in SCBF frames, do you think the post-buckling analysis needs to be done?
Very good question, in a sense that the question would be coming in terms of a split X kind of a thing, wherein the beam is there and you have chevron at the bottom and the V frame at the top. So here in this case, when a post-buckle case kind of a scenario comes in, if one brace goes off also, there is that, I mean, the post-buckle case, it balances out. So in a chevron, unbalanced vertical force comes in. In the case of split X, the unbalanced forces go off. Ideally, in terms of the codal language and all there is there in the literature, the split X is a better kind of a system, and the unbalanced force is also not there. The local evaluation is also not required. Basically, the post buckled and pre buckled is also not required per se. But what we have done in our analysis at local times is that it is not necessary that both the braces is going to buckle and go off. See, the idea is in the pre and post buckle, we are considering yielding to happen, compression to happen at one instant, post buckled is happening. But what we have seen during analysis is it's not necessary that one brace is like post buckle, the other brace might be still alive. So still unbalanced force might come in. So currently, as per codal language, what the person says is absolutely correct, that a split X is better. There is no imbalance force or unbalanced vertical force that is going to come. So local check is not required per se. But I say to engineers that take the worst case out of it. If one brace post buckles and one stays, uske case mein whatever may be the worst case that is coming, pick that and design.
Okay. Thank you, sir. So do you really think that the local analysis is necessary as per IS 18168? The question says, in case the structure is wind governing, even if not, how much higher than seismic should the wind be roughly so that we can confidently not consider the ductile provisions of the code?
You have a very good audience in a sense that these are the relevant questions in
They
a
are
case
mostly the practicing engineers.
Okay.
Yes.
Okay. Why it is relevant is because, see, if you say a structure is wind governing, then the question comes, do I need to follow any seismic code or anything like that? It is actually that you have to at least go for the detailing practices. Why I say is because the wind is just a direct force that we calculate, let's say for a certain case. The earthquake force is something that we reduce from the MC level to dB, then response reduction factor, everything comes in. So we are actually scaling down the earthquake force, and at that level we are checking. The earthquake force actually that might come maybe higher than what that is there. Currently, based on the load combination, maybe the wind load may be higher. So the easier answer in this case would be ki, let's say your building is governing wind case, no need to look at IS 18168, no need to look local checks or anything like that. But whatever detailing criteria that says, okay, certain connection has to be done this way or certain ratios has to be followed, that has to be followed.
Okay.
That is the only thing. Otherwise, wind, it's fine. You can go for hollow square sections for braces. You can do all and everything. There is no issue.
So the next question is related to R value. What is the R value to be used if there are different values of E by L?
No, for EBF system, they have given, irrespective of the link length, the EBF has been given as one value itself. They have not given different for, let's say, a flexure governing or a shear governing, etc. But however, as I said, the most stable behavior. See, if it would have been different, then you would start questioning what R value the moment resisting frame would be having, because it's exactly the flexural behavior that is there. So there is no question with respect to that. The only thing is the higher energy dissipation, the more stable is being obtained through short shear link only. So it is much better that way.
It's a very interesting question from Mr. Nirav. He says, do you have any online course which actually shows live examples using ETABS step by step with base model ready shared with all the participants?
I can make one. I mean, if the audiences are happy with the presentation and are eager more with this thing, I'll be more than happy to prepare one.
So I'll request all the
Specifically for
participants,
EBF.
yeah. So if they want to know more, maybe in the form of literature or maybe in the form of a video, they can write to you. And if there is any literature available where they can find some
You
procedural.
can give me a feedback form for this, and if they really want, then I can prepare one.
Okay, sure. The next question says, in the context of steel structure design, how do you compare the evolution of Indian steel codes with US standards, especially given concerns about the higher demand practitioners, conservative strength estimates, and limited research-based commentary in the Indian codes?
Again, I'm saying, see, guys, see, research in steel is very costly. To get material, it's much easier to do it in RCC and masonry. So when you have, see, you can always say that this particular code of 18168 has come, or I'll say inspired from AIC 340-116. It's always easy to understand that key when somebody has already run the race, we should not start from the beginning. We should start from what is the current knowledge, accommodate with respect to our steel, and then move on forward. So currently there is a lot of research going on in stainless steel, in carbon steel, in braces. BRB has been tested in IIT Delhi, Guwahati, Roorkee, etc. We are doing a lot of things. Change is coming. I'll prepare a commentary for this particular code. I mean, one is that session that is going to happen in December 5th. I'll prepare a commentary for 18168 so that it's once and for all done. And then accordingly we can have this thing. Things are changing, guys. I mean, itna bura nahi hai pehle jaisa. Things are changing. We have our own results of beam column joint. There are tests going on currently in IIT Roorkee with beam column joint in stainless steel, etc. So many things are happening. So I can vouch that there is IS 800 2007 is also getting revised. It's soon going to come out also. So things are changing. That's all I can say.
So the next point is related to IS 186/2023. It says this code is aligned with the other codes and demands model-based design with imperfections, stiffness modeling, and second order effects. Can you please throw some light on how this shift changes the entire workflow of steel structure design when you compare it with IS 800/2007, especially for industrial structures and multi-story buildings?
No, I'll say this. There is nothing as much has changed. As I said, you are still using limit state method. You're still designing for whatever effects comes from second order. Whatever you were doing as on doesn't change much. The only thing, as I said, is 18168 just expand section 12. Earlier, if you remember, IS 800 section 12 in EBF said refer to specialized literature. That was the only clause given in EBF for EBF system in IS 800. And for CBF and MRF, it's just 1.5 pages of clauses that were there. The only thing that has come with 18168 is right now, how do you assess the forces in the members? Which should be what force, what should be the value for which the column should be designed in MRF? That is all what this code says. It never tells you to kind of change the limit state method or change the design methodology. No, you're using your ETABS or STAD with respect to getting these forces. You are doing these local analysis. You have added a few load combinations to get the global analysis, etc. done. Nothing changes. Everything remains the same. Few changes here and there. Let's say slenderness ratio, lateral bracing near the plastic hinge region, extra requirement. If you are holding the top and bottom flange for the lateral torsional buckling near the plastic hinge region, then there is a higher demand, so higher section should be used there. If you are locally holding up in different location, what is the value of axial force to be used for the members, that is given. Few addition, I'm seeing more clarity has come. I mean, this work, if it have written as IS 800 itself would have come, then it would have been a little bit simpler. But another committee code came up with this particular code. That is why this confusion is coming.
Okay, sir. Okay. So the last two questions, and then we'll finish. What should be the design base shearing ratio or range between two systems if we use SCBF or BRBF with MRF or SMRF in the same bay as dual system along a particular direction?
Very, very tricky question it is.
Yes.
It has to be thought about in a sense that if you are using a dual system, I'm not sure whether I'll be able to do justify to the complicated question that it is. But I'm saying that in a dual system, refer to ASC 7, wherein it says what is the minimum base shear for which a particular system should be designed for, and go from that point onwards. Like if you are having dual system, minimum कोई एक system उसमें से कितना होना चाहिए उस basis पे जाना है. Now the question is, let's say in one system itself I have an MRF as well as in the same line of frame I have a CBF also. So it's a dual system. Which one would I want to depend more upon is the question now, whether I want to depend upon CBF or MRF. I would look at it from the point of functionality that I have a fuse that is a brace. If it gets damaged, I can remove it, I can move on. Whereas an MRF, if the beam fails in the same dual system, my problem after the damage has occurred becomes more for me. So the better is I'll give more onus to the CBF rather than my MRF. But as per 18168, currently the trust on CBF is not that much. So the question comes, that's what I'm saying. If you read more, you will get more trust on CBF. So if you ask me, I'll give more onus to CBF to take up the load, to get damaged more during the earthquake so that I can remove it and replace it after the earthquake. But current code believes more on SMRF. You will get your plastic hinge more in your beams, etc. After the earthquake, repairing will be very difficult. So all systems are good. Even SCBF, if you look at 341, it's good and as per that particular code. But ratio wise, nobody says anything. It is like minimum a certain level should be shared between the two. That's all. Like ASC 7 mein diya hua hai. They can start from there as their starting point.
The last question says, if we have with split X braces, we will be transferring the force to the intermediate height of the corner column instead of at beam junctions.
No. In a
How
split,
and what would be it effect?
in a split X, it is joining. The intersection is happening at the mid of the beam. Then the next end of the brace is at the corner of the beam column joint at each floors. So it's like crossing the two. So in no way it is coming and landing in the middle of a column anywhere. In any case, that will not be a split X in that sense.
So thank you so much, sir, for patiently clarifying all the doubts of the participants. Much appreciated. Thank you.
Thank you, Praveen. I'd like to say that the codal clause wise kind of a discussion will happen on the 5th of December.
Okay.
And if the participants wish, I'll make a, in terms of that line by line meaning of the codal clauses, and again give a kind of procedure for the systems. I can do that.
Definitely. And also you have already shared that there is INSDAG is already conducting
5th
one
December.
kind of an event in a
Yes.
similar line. So
Yes.
all the participants are kindly requested to register for that event and to get more insight about the topic. Vikas, it's over to you.
Thank you, sir. I believe all the queries from all the participants have been addressed. Now I would like to invite my friend, Mr. Akshay, to deliver the vote of thanks.
Greetings to all. I am Akshay, Master Students at Earthquake Engineering Research Center. It's my honor and privilege to deliver the vote of thanks on behalf of the entire Executive Committee of IIT Hyderabad Student Chapter. First and foremost, I extend our deepest gratitude to our esteemed guest speaker, Dr. PC Ashwin Kumar for his insightful presentation and enlightening session on design of structural steel systems as per IS 18168-2023. Today's webinar has highlighted the capacity design concept, structural system limitations and stiffness, material grade and ductility requirements, section and connection requirements. Moving on, I would also like to express our heartfelt gratitude to our faculty advisor, Dr. Praveen, for his continuous guidance and valuable suggestions throughout the planning and execution of this event. A special mention goes to the IIT team for ensuring seamless technical support and to the design team for their creative inputs and logistical assistance. I thank our program coordinator, Dr. Sunita Paliseri, for her continuous encouragement. I also want to express my appreciation to all the participants for their active involvement and thoughtful questions, which enhanced the discussions and made this webinar a collaborative learning experience. Lastly, I would like to acknowledge the hard work and dedication of the entire team whose collective effort has made this event a success. In conclusion, I extend my heartfelt thanks to each one of you for your participation and engagement. We are extremely grateful and looking forward to your continuous support in our future initiatives. Thank you.
Thank you.
Thank
Thank
you.
you, Akshay. Thank
Thank
you
you,
so
everyone.
much, sir.
Thank you,
The
everyone.
participants are asking about your video lecture recording. If I have a consent of yours, then we would
Yes,
like
yes.
to post this on the official YouTube channel of IIIT so
Yes,
that
please.
they can access the
Oh,
recording.
yes, no issues. Yeah.
Okay. Thank you.
Thank you. Thank you,
Mr.
Dr.
Ashwin.
Praveen.
Thanks
Thank you,
a lot.
everyone.
Okay. Bye.
Bye.
IT team, you are kindly requested to please stop the recording.